So, what about the elliptical galaxies we've been alluding to? Compared with spirals, the main difference is that ellipticals don't have a disk component. Here's the giant elliptical M87. It's the center of the Virgo cluster that we, namely our galaxy, and therefore our solar system and planet, is in gravitational dance with. We are bound to it. This is one of the most massive galaxies in the universe, about 1 trillion stars, although they can get actually much more massive than that as well. Well, an elliptical is basically a swarm of older stars. You notice the kind of reddish appearance it has, indicative of age in general, because they lack the dust and gas for ongoing star birth. There are no stellar nurseries going on in the ellipticals. They are the very largest galaxies, even though I mentioned most of the large galaxies are spirals. The very largest ones are ellipticals. They tend to be more numerous than the spirals when we consider that there are very small ones, dwarf ellipticals, in addition to the very large ones. So there's a greater range of size in the ellipticals than any of the other galaxies. Speaking of dwarf ellipticals, here's an example. Leo 1, part of the local group. Notice how basically dispersed they look. There's not a high concentration of stars. There tends to be less than about 1 billion stars in a dwarf elliptical. And right now we know of about 10 dwarfs in our local group, but it seems like we're finding more very small dwarf ellipticals. They're very difficult to discover in certain cases because the brightness and the stars of our own galaxy are hiding them. Well, here's M87 again, in the center of the Virgo supercluster, 50 million light years away. And the associated elliptical galaxies, many of these, most of the spots of light in this image are galaxies. The stars from the Milky Way can be seen from the little spicules of light coming off here, the optical effect. But no dust, no disk, no spiral structure. This is indicative of a very large cluster of galaxies. The center region of these clusters tend to be dominated by large ellipticals. Here's a dwarf elliptical. It's a satellite of Andromeda, M110. And the elliptical known as Centaurus A, it's kind of strange. You've got a thick dust lane, which is very unusual, probably from a collision event we'll discuss a little later. And then, in terms of galaxy classification, we have irregular galaxies. Here's some examples. These are galaxies that don't fall into the category of spirals or ellipticals or lenticulars. They're a little different. They seem to often arise from galaxy collisions or mergers with associated lots of activity associated with these galaxies, new star formation activity. Sometimes they're the dwarfs of larger galaxies. Here's the large Magellanic Cloud. We also have the small Magellanic Cloud. These are associated with our Milky Way galaxy. Often considered to be satellites, but not necessarily. They aren't necessarily orbiting our galaxy, but rather passing through. Here's a very chaotic core of the antenna galaxy, which is actually a merger event. We'll see that again. The small Magellanic Cloud. This is, again, an irregular galaxy associated with the Milky Way. I wonder what this thing here is. Any guesses as to what that is? Well, this galaxy, shown here, consists of several 100 million stars, several billion solar masses, which means there's a lot of large stars and gas and dust associated with this, about 7,000 light years in extent, 210,000 light years distant. This is the galaxy where the Cepheid variable period luminosity relationship was discovered by Henrietta Leavitt. Well, this was the answer to the little quiz question. It's globular cluster 47 Tucani, but it's a globular cluster. It may not have been immediate apparent to you, but that's what it looks like. It's a lot closer than the galaxy itself, 13,000 light years. If it was the same distance away as the small Magellanic Cloud, it would be a lot dimmer. Then we have the large Magellanic Cloud. Several billion stars, about 15,000 light years in extent, 180,000 light years distance. So it's a little closer than the small Magellanic Cloud, about 10 billion solar masses. Associated with this irregular is the Tarantula Nebula, one of the largest known ionized hydrogen regions. So it's a very huge region, about 800 light years in diameter approximately. Lots of interesting new star formation going on there. And here's an irregular galaxy, NGC 4449. NGC 1569, 11 million light years away, 8,000 light years across. A tremendous burst of star-forming activity associated with this irregular. So just a quick review as to probably the most important feature of galaxies, which is the gas and dust associated with them to produce planets and people and interesting things like that. So the spirals are rich in the gas and dust, which is very obvious in this image here, this edge-on view of a spiral galaxy with very dominant and very obvious band of dust. It's where the planets form, and it's where life can be supported. Ellipticals are almost devoid of gas and dust. In this high-resolution image, you don't see any evidence of the dust in these old star galaxies, almost all old stars. And then we have the strange occasional galaxy known as a lenticular, the disk, bulge, but no spirals. They're termed SO type galaxies, which leads us then to the galaxy classification scheme, which we will now turn to. So when classifying the galaxies, not too much complexity. For elliptical galaxies, E stands for elliptical, and they have a number 0 through 7. Well, E0 would correspond to a spherical elliptical galaxy as perceived by us on Earth, on through E7, which would be highly elliptical, very egg-shaped, very oval-shaped. So this is an E1 class, and this is an E6 toward the extremes of the different shapes for elliptical galaxies. So that's pretty simple. Spirals, relatively straightforward as well. We have S for spiral, and then a letter after that, A, B, or C. The A would correspond to a large nucleus with tightly wound arms, and as we progress through B and C, we progress toward smaller galactic nuclei and more loosely positioned arms. The arms aren't as tightly wrapped around as the B and the A. So that's it in brief. Now let's look at the standard Hubble classification scheme. So here it is, the Hubble tuning fork classification scheme. Tuning fork, get it? These tines here. Anyway, this is a nice picture that shows how as we progress in this direction through SA, SB, SC, we're going towards smaller bulge, more dust and gas associated with the disk component, and looser spiral arms. And here are galaxies, SA, SB, SC, galaxies in that classification. You can distinctly see the difference there. Large bulge, small bulge, but loose arms here. And then for the barred spirals, it's very similar. You just put a B after the S for barred. And there's a very large bar and fairly tightly wrapped arms. As you go to B and the SBC, you have smaller bulge and looser arms. So, and there are schematics of those classification particulars. And on the elliptical side, as we go toward smaller numbers, we're going toward rounder shape or appearance. And in the center is the SO, the lenticular. Galaxies are typically not in isolation, but in clusters. So let's discuss the clusters a bit. We have poor galaxy clusters. Our local group of galaxies, of which we are a member, here's the Milky Way, is in a poor cluster. Now that is not a demeaning statement or something that we should be disappointed in. Actually, we should be very happy about that. Tens to hundreds of galaxies in poor clusters, certainly under 1,000. There tends to be more spirals than ellipticals, or at least large ellipticals, in the poor clusters. And the reason I said we should be happy we're in a poor cluster is because in poor clusters we have a better chance for a life-supporting planet to exist. And there's reasons for that. One obvious reason is the gravitational instabilities of very rich clusters preclude the chances for a long-term life-supporting planet to exist. So that's a pretty happy thought. Then we have the rich clusters. Here's the Coma cluster as an example. Every spot in here, almost, except objects like this, which are stars in our galaxy, with the spikes coming off. Almost every image, every spot on here is a galaxy. So this is an extremely densely packed region of galaxies, thousands of them. This is an example of a regular cluster, which means it's evolved long enough to be essentially spherical in shape as the cluster, and mostly ellipticals in the central region. About 15% spiral or irregular types, and very crowded, which makes it very difficult for you to have conditions that are appropriate to support a life-supporting planet. Another rich galaxy cluster, the Hercules cluster. Looks a little different. Once again, almost every spot on here is a galaxy, thousands of them. This is an irregular cluster as opposed to a regular cluster. It's oddly shaped as opposed to more roundish. It hasn't evolved in its cluster structure as long. And it consists of mostly large spirals. Well, spirals often are large, but mostly large spirals in this as opposed to ellipticals. So that's a significant shift and is the key characteristic making it an irregular. Lots of collisions going on, as you can see here. Lots of events where galaxies are interacting with each other. And that wreaks a lot of havoc in the cluster. Now, just as the galaxies don't form in isolation, so too the clusters of galaxies do not form in isolation. So we have clusters of clusters, known as superclusters. Some of the largest structures in the universe consists of dozens of clusters. Now the clusters themselves within a supercluster are not bound together. They tend to be drifting away from each other. Moreover, the superclusters, many of which are shown here that we know of, here's the Virgo supercluster and other close superclusters of clusters, those superclusters are likewise not gravitationally bound to each other. So the whole thing is drifting and changing and yes, interacting with each other. The whole structure is gravitationally being altered by not only each other but by additional matter that is unseen, known as dark matter. But these superclusters tend to be about approximately 150 million light years in scale. And so we see more and more detail about the way in which these superclusters are progressing, developing with respect to time. So our understanding of the superclusters emerges from measurements of hundreds of thousands of galaxies from their redshift. The further away a galaxy is, the more it recedes from us. We'll address that shortly. So that large-scale structure can be mapped on scales that are very vast. And these wedges shown here actually take our view out to about 3.5 billion light years as we go across here. So it's a significant portion of the observable universe. It's difficult to get data from real far away. So it looks like it's the density of galaxy clusters is diminishing out, but that's actually a selection effect based on our technology. But at the largest scales, we see that the distribution of the galaxies seems more and more uniform. And actually a pattern emerges where we have superclusters that reside on the edges of these great voids. We have kind of a sponge-like pattern of superclusters surrounding voids that are about 100 to 400 million light years in extent. So that's our current picture of the overall structure of the galaxies in our universe. How many galaxies do we have in our universe? What information do we have that lends information to answer that question? Well, the Hubble Space Telescope, certainly the most famous telescope of all time, has given us some direction to answer that question. And in the 90s, there was a project called the Hubble Deep Field. What it did is looked at a little spot over near the Big Dipper, and here's the spot in the sky in reality. What they were looking for is a tiny patch in the sky that was not filled with Milky Way stars, because basically they wanted to hold the shutter open, like on a camera, and stare at this spot in the sky for a long time to let photons accumulate and see as deeply into the cosmos as possible, thus revealing the galaxies that are in this tiny spot of the sky. So if you looked at this spot through a regular small telescope, you'd likely see nothing. But if we magnify this 50 times, we have all these stars in this region. So that's 50x magnification. It's a really small spot, and within that small spot then, a small region in there that has none of those stars, or almost none, was chosen. And this is what's magnified here. And this is the result of the Hubble Deep Field. A 10-day exposure of this tiny patch of the sky. 2/millionths of the sky was covered in this image. 3,000 galaxies were discovered in this tiny little speck of the sky. Keep in mind, it's this small region that's within this small region, and 3,000 galaxies of all different shapes, sizes, ages, luminosities, colors, characteristics. It was one of the most famous images in space of all time, and to this day is informing astronomers about the nature of galaxies, galaxy structure, and also how many galaxies we actually have in our universe. But we're not done with the story yet. The story, part 2, comes from the Hubble Ultra Deep Field, which essentially eclipsed the results of the Deep Field study. And here it is, another blank portion of the sky, the Hubble Ultra Deep Field project, near the Fornax constellation. The data was taken from September 24th, 03 to January 16, 04. This blank sky area was about 1 square millimeter at 1 meter. If you extend your arm out and put a dot, think of a little dot, a period, well, a 1 millimeter square, which is just a small dot. That's the dot on a sphere surrounding you of 1 meter radius. A very tiny little dot on the entire sphere of the sky that's observable. This was an 11.3 day exposure requiring 400 orbits of the Hubble Space Telescope. It saw 13 billion light years into the cosmos, which is almost the extent of the observable universe. About 9,000 galaxies were discovered in this image that is now displayed. Galaxies that are viewed all the way back almost to the beginning of time. It corresponded to 1/13 millionth of the sky. So it would take 13 million patches like this to fill that entire sky view. It would take the Hubble 1 million years to do this, so it's not likely to happen. But this is not a unique patch of the sky. Other than that, there's not many Milky Way stars obstructing the view. For other reasons, we know, the deep field and other surveys that have been done, that this is typical, that the galaxies shown in this image which is the deepest image of galaxies ever taken by humans, is what we would see everywhere in the night sky. So we see galaxies that are almost out of view. Not actually all of them are seen here, but the very oldest galaxies, the greatest redshifts, indicate literally about 13 billion light years of distance, and therefore age as well. The conclusion is that the Hubble would be able to view over 100 billion galaxies in the observable universe. So we know from this how many galaxies that there are in our universe that we can see. However, the number is probably larger than this because of all the very small dwarf ellipticals that we're just learning are much more plentiful than we knew before. So that's pretty impressive, and I wanted to take the time to take you through that so you can just see how incredibly massive our observable universe is, how many galaxies we actually have within it. This graphic shows the extent of those two surveys. This is a timeline from the Big Bang beginning out to the current time now. The Hubble Space Telescope, doing the Hubble Deep Field, went all the way back to approximately 1 billion years after the origination of the universe itself. The Deep Field saw so deep into the observable universe that it was about 500 million years when galaxies were first forming. Now, some of this may seem confusing to you. Keep in mind this is a nonlinear scale. Almost all the time is right in here. We'll investigate the beginning of the universe, and that'll make more sense. However, as we look deep into space, we're looking back in time. So this time frame of 500 million years after the universe began is consistent with the depth of the light that the Hubble was observing when it took the images of those galaxies.